All right, so I have spent a lot of time talking about the kind of things that are good for simulation I/O. There's often a collective read or write of data. There could be some weird workloads, but the data pretty much goes from the start of the file to the end of the file. Processes are not going to backtrack or randomly jump around in the file. And with MPI being standard for 3 decades and MPI-IO being standard for 25 years, there's lots of opportunities to get into the software stack and help out all these applications. Now, AI looks a little different. In AI, we're going to generate a network one time, but then we train the AI against that workload, against the training data set, and there's repeatedly read that data set over and over again, figuring out is this a dog or cat or whatever the answer is, and it is kind of random. You've mapped it. You load this data set by hopping through the file in a fairly arbitrary way, almost from the sake of the file, from the perspective of the file system. And sometimes the whole workflow is many different applications. All one piece is collecting the training network. One person is feeding the next consumer, feeds the next consumer, and it can be more task oriented than application. And as I said, as I was putting together this talk, there's got to be something we can talk about in terms of machine learning, and some of my colleagues say, hey, you should look at DLIO. It's Hari Devrajan, when he was a student here at Argonne or a research aide a couple of years ago, was working with ALCF folks to put this together. And so I don't want to pretend to speak authoritatively to this. I was sort of relatively new to this topic, and I'm probably going to get some details some wrong, but please check out the documentation posted on our ALCF page and the DLIO GitHub page and Hari's CC grid paper and the other work he's been up to. I'm speaking more to advertise it than to speak as a developer or anything. I don't want to take credit for developing this, but here's the deal. DLIO is not itself doing machine learning. It's a machine learning benchmark. So you generate some synthetic data, and then you can train different workflows against that synthetic data, or you can experiment different ways. In this figure over here, right, we've got config files that describe the kind of workload that we're going to do, and there's some fake data. And so the DLIO developers looked at some of the popular machine learning frameworks, the TensorFlows and the PyTorches and whatever else is out there, and captured the behavior in these configurations. And then when you want to study the behavior of these machine learning frameworks from an I/O perspective, you can set them up, and then the DLIO will call into these different Python-oriented now frameworks and do the I/O the way that these frameworks do them. It's not trying to mimic the I/O. It's sending up the requests so that the frameworks do the I/O the way that they would do it in a real machine learning workload. And so what's been great about this is that you're able to try out different configurations for the file system or the way that they do the I/O, reading or writing. And from the paper, there was this experiment. They were rapidly able to test out different configurations for access sizes. They found a point where, for the UNet 3D case, an access size about 1 megabyte was the right thing to do. We could try compressing the data, different sizes, and you can see the best compression ratio for this particular data set. I would have loved to show you some Darshan data, and I ran out of time to collect that. There's something odd going on with the way that DLIO does the I/O versus the way Darshan expects I/O, and so that's okay. That's a selling point. I'm happy to talk about negative results. We need to get Darshan better at understanding machine learning workloads. And so having DLIO not work with Darshan out of the box is a great learning opportunity for a tool like Darshan. So, these trace graphs that are here are DLIO provided graphs. The DLIO will report its IO phases versus training phases and record in a Chrome performance graph that you can load into a web browser and it's scanned through in a timeline fashion. You can see the different phases and how different workloads behave. PyTorch is going to behave differently than TensorFlow, for example. And so what would be great, DLIO has some facilities for tracing, for recording the information, and we can tie that into Darshan. Now we have a even more complete picture of what's happening for a pretty important and growing workload on these computers. So there is a lot of, sorry, I'm pausing. Like I said, I was just surveying DLIO, but maybe you know more about DLIO than I do, and maybe you'd like to talk more about some of its features I may have missed. Well, I'm happy to learn more about this exciting framework. So yeah, machine learning is definitely one of those areas that is going to be, so like I said, we understand, maybe we don't get it right all the time, but we sort of understand the problems with simulation IO. Machine learning IO provides a whole new ecosystem of tools to learn about and to work on, and it's going to be, it's why I like working this job. There's always something new to figure out, and right now the puzzle is how can we make machine learning IO, how can we understand machine learning IO better, how can we make it better, and what storage, and by answering those questions, we can contribute to the better design of these machines as they provide the different workloads that are going to be used on them. So we're getting to the end. I really thank you for your patience, but we got a couple of things I want to talk about before we wrap up that I didn't have time to cover fully. There are other, if I'm sitting down to an application and I want to figure out why is its IO not very good and Darshan isn't quite doing it, I might even go down to something like L-trace or S-trace. These routines capture system calls and library calls and report out in a very verbose fashion what the application is doing. And sometimes that's helpful if I want to confirm that, say, the Cray library is actually making the kind of call I think it's making. Cray is a commercial vendor. They don't have the source code for their MPIO modifications. So sometimes I got to poke around their code through more indirect fashions. That's fine. It's just another tool in the toolbox. And sometimes IO performance is more prosaic. We talk about why collectives are so useful, and sometimes we can't use collectives because not everybody is participating in that collective. Well, with GDB, the good old debugger, right, that we use for all kinds of applications, I'll sometimes attach to a running process that seems to be hung and try to figure out which process is participating in the collective and which one isn't. And if I see that some process did not participate in the collective, I can figure out why, and we can change the code a little bit so that everyone ends up being in that collective call. I didn't get a chance to talk too much about GPU programming with respect to storage, and that's also going to be a big change in the landscape pretty much now, I suppose. NVIDIA has something called GPU Direct for Storage, and where you can initiate storage transfers from the GPUs. We can imagine an IO stack component like Romeo picking up some pieces of that and directing more of its IO from the GPU. But that's something I need to learn more about myself, and before we can start making some changes there. Also exciting in the landscape, this DAOS file system is Intel is going to deploy DAOS on our Aurora system and probably some other ones that are out there. And it's quite different from the Lustre file system. It's the acronym DAOS stands for Distributed Asynchronous Object Storage. And the fun part about it, just in quick summary, is that unlike a legacy file system that provides a POSIX interface, and we have to figure out how to write to that file system quickly, DAOS has a native interface that's unlike any other interface programming wise, which is fine. The MPIO driver, our friends from Intel, contributed a Romeo driver for DAOS, and so we can still do MPI file write and file read from DAOS objects, and the MPIO driver, the Romeo driver, will figure out which I'm going to get the terminology wrong, but which DAOS object contains that information and where to go to get that data. And so as we use these high-level IO libraries like HDF5 and in turn MPIO, these brand new file systems like DAOS will be transparent to an extent to the user. Of course, there's always room for tuning and optimizations, but in terms of actually interacting with these new technologies, it won't require entire code rewrites. We'll just, the changes will be a matter of a little bit of tuning parameters. So 3 hours to talk. What if you come up with nothing else? There's a lot of different software layers involved in IO. Maybe as we log into a new machine and do an experiment, you might get some poor IO performance. But tools like Darshan, using libraries like HDF5, these all help folks like me, who I think about IO libraries and file systems. By using these high-level libraries, or by using Darshan, we can take that data and that workload and talk in terms of that application scientists understand. So, but if I work with high-energy physicists, I don't know much about the Higgs boson. It's exciting that they maybe tracked it down, but in terms of simulating it, right? There's a lot of math involved, but in the end, they write to an HDF5 file. So I can make that HDF5 file write data or read data really fast. That's a common language for us to meet in the middle. Also, I want to point out before I go that all these sites, ALCF, Oak Ridge, NERSC, there are people on hand who love solving problems like this, who know all the tuning parameters, or if they don't know every tuning parameter, know how to talk to me or people like me. And this is, there's no need to suffer in silence if you have poor IO behavior out of the box. We can all work together and figure out where the problem lies. It wouldn't be a talk if I didn't have a big page of acknowledgements. I've given versions of this talk with colleagues at supercomputing and at ATSPESC, and I use the Cray machine, Polaris, a lot. So thanks to ALCF for taking good care of a complicated machine. And this whole work is part of a BSSW fellowship, so I want to make sure I acknowledge them. Before I sign off, if anybody have any questions, we can talk a little bit about anything on your mind. Well, thanks. This video is recorded. It's all going to go off to Argonne's editing. We'll try to get things looking pretty, and I'll put it online so we can all enjoy this in the future. Thanks for your time, and I hope if you have an IO problem that this helped you understand your next steps. Thanks a lot, everybody. Have a good day.